Okay, let me briefly introduce the idea of adding color to these plots where you have iterated function systems. And you did the Fern last time, so let me start with my version of the Fern program, which is down here. So you'll be creating this later. All right, so here's my code for the Barnsley Fern, and I hope that some elements of this program will be familiar to you, and I'll try to explain what I've added. All right, so first of all, close all, clear all. That closes all the plot windows and removes all the variables. I defined nseq equals 40. Now you remember that to generate the Fern, you generate different sequences of points. Each sequence starts from the root of the Fern. So I have 40 sequences of points. Probably you want to have more to have a nice Fern, but I just did this because it will execute quickly. And iter equals 20. That means each sequence has 20 points in it. So you can see the comments over here which explain the statements. Okay, I'm starting at 0, 0. I start each sequence at 0, 0. Zi is going to be all of the points that I generate, and Ci will create a color index. And the color will depend on which function is used in the iteration. Now, if you remember, in the Barnsley Fern, there are actually 4 functions used, which are exemplified in these 4 if statements here. This one is the first if statement, which corresponds to this function. The else if is the second and corresponds to this function. This else if corresponds to this function. And the last else if corresponds to this function. Now I'm assigning a number to each one of these functions. The first function, I have c equals 1. Second function, I have c equals 0. The reason I did that out of order was that the second function was the one that was most probable. It had probability 0.85. So I thought that that would probably be the best to put as the first one. The next function has color c equals 2, and the last function has color c equals 3. So every time I iterate, that is, every time I generate a sequence, I'm going to iterate. I choose a random number, and depending on that random number, I choose one of the 4 different functions, and each one of these functions has a color, and I record the color, or the color index information. At the same time, I record the location information. All right, so as I go through this loop, I'm recording all of the positions and all of the corresponding color information. All right, so now I want to do the plots. I'm actually going to do 4 different plots, and the plots are going to use different color information. All right, now let's look at when j equals 0. And this says figure j plus 2, so that means it will be figure 2. Now, what I do here is I shift the color information by j. Now, since j is 0, I don't shift the color information at all. So the color information here corresponds to the function iteration, corresponds to the function used in the current iteration. This is the plot command that gives you color. So let me explain this plot command. Scatter 3, it's actually a 3-dimensional plot. Here are the x coordinates, the y coordinates, and the z coordinates. Now I'm not really interested in the 3 dimensions, so all of the z coordinates are 0. That's why I multiply 0 times c, q, 1 through n. If you wanted a 3-dimensional plot, you could take out the 0, but you get a fairly nice plot even when you don't do that. All right, so these are the x coordinates, which are the x coordinates of the position that I generated, y coordinates of position. This is the z coordinates. 3, that gives the size of the marker, and this is the color coordinate. Now, what the program will do, it was automatically assign colors to the different color coordinates. Now, we know the color values are going to be 0, 1, 2, or 3, so it's going to assign colors to those values. Typically, it assigns a deep blue to a low color, and then it assigns a more reddish to a higher value of the color index. Now, that's when j equals 0, it will use the current color information to plot the colors. Now, when j equals 1, it will plot the previous color iteration information. So the color depends on the previous function that was used before the current function. When j equals 2, it's the one before the previous, and so on. All right? So that's gives me my first 4 plots. Then the really interesting plot is this exponentially averaged color. Okay. Now lambda is my exponential constant. I'll explain how this works. I'm going to define a new array to hold these different color indices. These color indices are computed based on the colors that I generated, that I saved as I generated the fern. The first color is the same, and then as I continue, I take this weighted average of the current color and the previous averages. Now you can adjust lambda, you can use different values of lambda, and that will change the nature of the average. Now, unfortunately, when I do this, this should be enough, but unfortunately there are some technical details that you need to take care of in order to make the colors look nice. What this does is it changes the, when you do it this way, you get some very outlier values for the color. So what this does is it removes the outlier values, and it just puts the colors in a nice range. I also noted that unless you discretize the colors, it takes a long time to plot. So this bins the colors into 256 different levels, and the plot takes somewhat less time. And then this figure, I make this figure 1. This figure plots the colored fern. So let me show you how this works. Okay, so you can see that I now have my code in my Octave window, and I'm going to go ahead and execute. So you can see this is figure 1. That's the one with the averaged colors. This is the one with, so you can see these other ones are different versions of the other colors. So if I wanted to make this, flatten this out so I can see it, here's the actually colored version of the fern. We can talk a little bit more about what this actually means. You can see that these ones, this one is iteration -1, this one's iteration -2, and you can see the differences. Iteration -2, this one's moved up, this one's moved down. So again, we can talk about what that means. And as I said, the average colored one is the pretty one. You should try doing this with more points. So there it is. Okay, let me just say a little bit more about this. When you do your program with colors, you can just basically copy and paste this part in to reprocess your colors. Whatever vector your color vector is, you can replace CA with that color vector. So you may not fully understand what's going on here, but this is just to make the colors look nicer. The other thing I would like to say is that to create this plot, this was from the Sierpinski triangle, or the Sierpinski gasket, but with one of these with the swirl function. Now, so what do I mean here? Replacing this equation here with this equation here. If you looked at the Barnsley fern, that would take place in these places here, 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 and here, and also here. What you would do subsequent to this step is you take a function of this z. So for instance, I would do something like this. Z equals, I called it VFN of z. Okay, so that would redefine the function. So this redefines the location. Now this, would define this v function as a separate function file. You know how to define functions, and in order to create this, create the picture up here, you would use the function file that's called swirl, and that's on page 5 of the PDF. So in this program, the change is minimal, but you do need to define this function v according to the specification in the Flame PDF. Now I like to do it this way because then it's easy to change this function v and get different distortions. Like you do swirl, there's one called horseshoe, and so on. So that's a feature that you need to add to your program.